Hello everyone! In this video we will continue to examine topic 12.1 and in particular we will continue to examine the Bohr model. Alright, so now that we have two important results, quantization of angular momentum for the Bohr model of the atom, as well as the quantization of the electron radii, we're going to turn our attention to the most important application, which is to figure out what's going on with the energy. And remember that the total energy is said to be quantized. So that's where we're headed. So we're going to come back to this relationship here. This is our Coulomb's law relationship for a uniform circular motion orbit. And we're going to observe that, in order to get the energy, we need expressions for both the kinetic and the potential energy. And to do so, we're going to use a couple tools that we will really develop in topic 10 a little bit later on, but we need sort of right at this particular moment. The first is to see that from this relationship, we can get a pretty straightforward expression for the kinetic energy. So if you take this relationship and you multiply by r over 2 on both sides of the equation, you will get 1/2 mv squared on the left-hand side. And on the right-hand side, you've multiplied by r over 2, you get this expression, 1/2 k q1 q2 over r. Notice one of the r's is canceled, and so you no longer have r squared, you just have r. And that gives us our expression for the kinetic energy for this electron in orbit. Okay, and this is actually a general relationship for any orbital kinetic energy based on an r squared law. So this and its equivalent for gravitation also applies. We then need an expression for the electric potential energy, and that's a little more challenging. Okay, and I'm going to go into this derivation in topic 10, but suffice it to say that what we're doing is we are integrating over a changing force. So we originally introduced our idea of work as f dot s cosine, or f dot s or fs cosine theta. What that formula presumes is that the force and the displacement are constant and have the same directional relationship to one another the whole time. But in truth, that may not be the case. So what we actually need is to capture the fact that for every little bit of displacement, ds, the force might have a different value. And that's why we're going to use this integral formulation here. So without going into the details, f is a function of r, that force changes, but we have an expression for the force as a function of r. And what we're going to do is we're going to observe that the electric potential energy will just be the work done against the Coulombic force, bringing a test charge from infinity to radius r. And that's exactly what this integral captures. Don't worry if you don't have integration yet, but the final result looks like this. So the electric potential energy is negative, as it must be for a bound state, and it's equal to negative k q1 q2 over r. Notice the similarities, but not identical nature, of these two expressions. So this is the electric potential energy of that electron in orbit around the proton. Then, straightforwardly, we can find the total energy of the electron by adding together the kinetic and potential energy. That gives us this expression, minus this expression, because there's a minus sign here, and is therefore equal to minus 1/2 k q1 q2 over r. And then finally, we're going to simply insert the allowable radii, okay, as a function of n. So the r sub n, go right in here, and you get this massive, annoying expression, which we then rearrange like so, and notice that even at this point, you can see the end is in sight. Notice this is a negative 1 over n squared times a whole bunch of constants relationship. And that negative 1 over n squared, that captures our quantized energy levels of the hydrogen model of the atom. And in fact, this is the equation that we need to predict the spectrum, or the emission spectrum of hydrogen. Notice that the only thing that changes that total energy is n. So our different energy levels are represented by n equals 1, n equals 2, n equals 3. And remember that n, this original n, came from this assumption. It came from the assumption that the only allowable stable states were these standing waves with integer numbers of wavelengths around the proton. And not only that, but we also have an expression for this constant, which we have known for a long time. But as it turns out, that constant is not fundamental. It's not an extra constant in nature. It's equal to this mess. 2 pi squared times the mass of the electron squared times the charge of the electron to the fourth times k squared. Notice we could unpack k as 1 over 4 pi epsilon naught if we really wanted to, divided by h squared. So this whole mess of constants, as it turns out to be exactly 13.6 electron volts. And this is the smoking gun. This says we must have been doing something right because this was an unasked for prediction, right? We had no idea we were going to end up with this. And all we needed was this concept of the wave function to do so. It's really quite astounding. It's as if you had sort of this fundamental constant in nature, and then suddenly you discovered, that there was another way to calculate it, that it was dependent on other things. And that calculation allowed you to sort of test this really wild, novel theory. And it turns out to be true. So this is a crazy result. And in fact, this is the result we have seen before. So by assuming the electron can be described by a standing wave, psi, we can derive the exact values of the measured emission spectrum of hydrogen. And I'll let you work your way through this. This just says the frequency of any of these transitions is the difference in the energy levels divided by h, which is therefore the difference in the negative 13.6 electron volts per n squared of the two n's for the different states. So if you're going from 3 to 2, this ends up being 1 over 9 minus 1 over 4, for example. And all of this comes from that mess of constants that we derived in our application of the wave function. Okay? This is a wildly successful theory, incredibly important to the history of quantum mechanics, and it stems almost entirely from classical physics, combination of things we already knew, plus this identification of the electron as the wave function here. And it gave us an incredibly precise prediction, quite unexpected in nature. So each of these values pop out of this equation in a way that we had measured prior to this, but we had not understood. We did not know where these values came from, and we just derived those particular values. I'd recommend working your way through some reminders for the Bohr model of the atom and the conceptual questions here.